When we talk about our sellers, they're usually integrating with us by putting little tracking pixels on email newsletters, similar for web, or integrating with our mobile app SDK that we distribute and allow you to kind of integrate with us on iOS or Android. These two methods of accumulating data, you'll find, are very challenging because of their scale. Okay, so we have, first of all, live web traffic. We have a variety of web integrations, as you just saw. They're part of some very high traffic websites and platforms, like, for example, commenting platforms, these web integrations kind of amount to 25,000 requests per second. It kind of ebbs and flows throughout the day. Actually, it's funny because most of our traffic is in America. It kind of peaks around like lunchtime when everyone's on the internet, and then kind of, so not only do we receive a large amount of hits per second, but we also have to respond to those requests, ideally in 500 milliseconds or less. So, and that includes connection overheads, TCP overheads, SSL overheads, and that's quite difficult. Moreover, the integrations should never present any kind of error. Like, even if everything is broken on our end, we must return 200 OK, or else people will notice, and people may take us, publishers who receive a lot of traffic may remove us from their site because they'll begin to potentially receive errors or receive complaints from their audience. These integrations generate about 500 gigabytes a day of data to us. Keep in mind, of course, not all of it is unique or useful. You have a lot of repeat visitors to the same site, and we have to kind of grin and take it, even though we know we're not getting too much value from it. We need to still accept that traffic because one day there could be a useful ping. Yes, so that's all I have to say about our API, our web integrations. The next style of us taking data is the batch integration, and in this batch style, people upload files directly to us. We tend to receive about 100 gigabytes a day from our sellers, and this data tends to be more useful because it's like explicitly curated data for us from the seller. It's not just like a fire hose of web traffic. It tends to be more useful. So we get about 100 gigabytes a day of that, but because multiple buyers are interested in receiving that day's data in their own format, we kind of amplify it. We convert it like 5 times over into various different partner formats, and then we upload it to their S3 bucket or SFTP server. So roughly speaking, I would say that outgoing, we've got anywhere from 500 gigs to 1 terabyte a day. So that's pretty big, and all of this needs to work well, 24/7, and be able to adapt to variable amounts of demand. Okay, so now let's spend a few minutes talking about the software that we built to solve these problems. I think this will give you the context to understand why we decided that deploying to a container platform, like a container management service, really made sense for us specifically. So here are some of the underlying tools that we built that make our large rate of data ingestion possible through the avenues of web integration and batch. So first of all, we got a high performance HTTP API service. This, has to kind of play by those rules of like, take a lot of requests and returning 500 milliseconds or less, never returning an error. We've got an incoming data transform and filter from our sellers because they are sending us data in various types of formats, JSON, CSV, TSV, what have you. We have a log-based event store. It's built in-house. Our CTO built it. It's kind of like Kafka. It's a lot simpler. I won't talk about it in this talk because you can make a whole talk about it. We have outgoing data transformation and filtering to our buyers. So once we've gotten the incoming data and put it into our own format, like a normalized format, we then denormalize it and put it into the buyer's format. Finally, due to the scale of data that we receive, understanding that data is very, very difficult. It's still very difficult, but we have some data aggregation tools that kind of look at all the stuff coming through our system and generate some aggregated rows and columns that kind of say, okay, you got this many hits of this type on this day. It sounds simple enough at a bare bones level, but I think it all becomes complicated when you see the scale that we see. So, roughly speaking, we tried to build all these apps that you just saw to conform to something resembling the 12-factor principles. And I wrote these slides before I saw Casey's 12-factor talk yesterday. And so it seems a little repeated now. However, I did kind of pick at the time like 4 mononyms, like 4 single words that I think kind of best express the qualities of the software. And those are scalable, identical, expendable, and fair. And they can be mapped to 12-factor principles. I'll leave that as an exercise to you to figure out what those are. So for us, scalable means that you get a linear relationship between the number of replicas of the program that you're deploying and the total performance of the replica set. Identical means you don't have to create special configuration for any replica that you create. You can run the same command 5 times in the infrastructure or the cluster, and you'll get 5 distinct workers, no sweat. And of course, that lines up with the scalable goal, right? Because if you have to create some kind of unique procedure or distinct configuration for each of the 5 replicas, then scaling is no longer a mindless job. You have to work hard to scale up and scale down. The third principle is expendable. So replicas should tolerate sudden termination. So more importantly, the cluster should tolerate the death of a replica as well. So they should be able to see that the replica died and kind of swoop in and take care of the stuff that was dropped on the floor. Finally, we have fair. Replicas should strive to distribute the work items that they share evenly, as evenly as they can. So if the shape of the cluster changes on you, for example, if an expendable replica was tossed out, then the distribution of labor needs to change as well, and do so in a timely manner. And that's a similar goal to expendable, where when you kill off a replica, other replicas will jump in. So what do we write those tools in? You know the principles now, kind of what we're building now, how do we build it? So we used Go. We built all those tools using Go. We then packed them up into Docker containers. We found that Go and Docker were a really good match because, first of all, talking about Go itself, Go is great for our use case. We have a lot of fast networking that we have to do. It's very good at that. It has very good primitives and a standard library that supports HTTP serving very, very nicely. And it also handles concurrency very nicely. So it scales well to dealing with a lot of concurrent requests. So as part of the major part, since the major part of our business is a web service, that was super useful to us. When you combine Go with Docker, though, that's pretty natural too, because when you compile a Go binary from source, you have to compile it. If you didn't know that, you end up with a single binary that usually is freestanding. So imagine if you had like a Django web app, you would have 10 Python files that are your source code, and maybe 100 other files that represent your library dependencies. They don't travel easily. You kind of bring them all together. You might be able to put them in a zip file, but with Go, everything with a main function compiles down to one binary. It might be a very big one, but it's still freestanding. So in terms of integrating it with Docker, that was very easy for us because all we did was build a base image that supports a few of the libraries that we need for everything. And then we simply take that base image and overlay a single file in it, and we were done. That was our deployment, and we could run it anywhere. So now that you understand the tools we built and how we packaged them up, let's talk about how we deployed it the first time around. We used a piece of software called Fleet. So what is Fleet, and why did we choose it at the time? So a little history lesson, and it's very, very recent history. So just 2 years ago, the idea of container cluster management was pretty immature. Kubernetes was pre 1.0. It was not something that we were considering using for a production stack. So the predominant line of thinking at that time was, if you need a container management system, take a normal cluster management system, and instead of running normal programs on it, run Docker with it, and run your workload with the Docker command. And as you can imagine, there are a lot of caveats, there are a lot of manual things you have to do. That said, it was what we had, so we kind of just bent it into shape. So in that realm of generic cluster management systems that we were considering using for launching Docker, the two players at the time were Mesos and Fleet. Fleet was what we landed upon at the time. So that's an integrated component of CoreOS. CoreOS is it's a company, but also it's a distribution of Linux that's meant for use on cloud computing infrastructure. It does many cool bells and whistles these days. At the time, we just use it as a kind of a container running base image. Fleet is a tool within that just lets you distribute systemd unit files to nodes within your cluster. So what unit files are, what they are is just kind of config files that tell you how to run a given service and how to monitor that it's still working and what to do before you start it and what you do after you start it. So classically speaking, you would use a systemd unit file to launch like Apache or a database or something like that. So to use it as a container management system, we had to write systemd unit files that launched Docker, the program. Yeah, so by the way, since they're here today, I should note this is no longer CoreOS's recommended platform for running containers. They have Tectonic now, which they've adopted Kubernetes, and so Tectonic is their product that's on top of that, that's for the enterprise. So I just mentioned that because Fleet is probably not what they want people to be talking about at this point so much. So here's just a quick example of what I'm saying with a systemd unit file. So the important part's right here. You can see that there's 3 commands. The thing to do before is to grab the Docker image for the, for example, our API service. To start it, you call user bin Docker, you give it a bunch of parameters, and then you give it like the command line and the image name of what you want to run. And then at the end, there needs to be like a piece of lifecycle that deletes the stopped containers. So there is a Docker RM command at the very end. And of course, if you forget any of these steps, then you might end up with a situation where it won't work because too many old images piled up, or you forgot to pull the latest stuff. There's a lot of places where this can fail out. So what we found with Fleet is that it presented a really imperative way of scheduling anything. There was a lot of individual commands that had to be done to achieve an overall net effect. So let's say we wanted to bring up a new version 02 of the food service. First, you had to submit a unit file, and then you would start the first replica of it. So you run a submit and start. And so that's for example, if you have 1 replica. If you have 2 replicas, you have to do fleetctl start foo version 2, number 2, number 3, number 4, number 5, up to as many replicas as you would end up. It was very manual, and it was a little troublesome because, well, I won't go into because, but for stopping an old unit, and you'd have to do the reverse, right? If you wanted to bring down all the replicas of an old version and bring up new replicas the same number of replicas of a new version, you have to stop, destroy, submit once, and then start a bunch of times. It was also sensitive, right, to the order, right? Because what if you don't want to stop all of these things at the same time before starting on the new ones? What if you want to stop one, start one, stop one, start one? All of this had to be manually implemented by a human. So it was very difficult for us. So overall, let me just talk about like when we were with this system, what did we like about it? We liked CoreOS a lot. CoreOS is pretty much simplifying it. It's a read-only operating system that provides easy upgrades. So it kind of upgrades itself, and a lot of the inner workings of that are not really exposed to you. It just kind of works. And I think they still kind of follow that pattern today. They're offering products that keep themselves up to date. Security is one of the most important principles. The next thing that we liked was that we didn't really have to install anything, invest any tech effort into installing Fleet, because that was bundled with CoreOS. And that just made it a kind of a no-brainer. When you add a new node to a Fleet cluster, well, that's pretty easy. All you need to do is specify where the configuration server is. So it uses a configuration store called etcd to kind of coordinate between machines. So all you have to do is power up a new node and point it to the etcd server. And boom, it was part of the cluster. So we could start accepting units. Finally, the last great thing that we liked about it was that it contained a well-understood format for unit files. Systemd. Some people hate it, some people love it, but like it or not, it's definitely a standard in the open source Linux industry at this point. So it was something that people could know and jump in on and kind of understand what its boundaries were. So what didn't work so well? Fleet had a number of rough edges for our use case, mainly centering around the fact that it was not designed to be a container management system. So as I said before, scaling was very difficult. You'd have to explicitly number the replicas you want to start. So you could have, and the numbering wasn't really enforced. So you could start replicas 1, 3, and 25, and you'd have 3 replicas. Right, you couldn't hang your hat on like, what is the greatest replica number in the system? You don't have 25 replicas, you have 3. So because there was no kind of enforcement at that level, it was very difficult to perform scaling in a very easy way, even with our own scripting. Releasing was very manual. Again, the same reason. The light support for replication and the fact that you submit, stop the old stuff, destroy the old stuff, so on and so forth. Very, very manual. We didn't have any service discovery system. So just in defense of Fleet, why should it? Because Fleet did not even advertise like how the units should be able to talk to each other. That just wasn't in its contract. So we needed service discovery. For example, to discover a database dependency that we needed, we didn't want to explicitly bake it into the configuration of the unit, so we needed it to be able to help us find other units and what their IPs were and so forth. So there was none of that. We ended up using a third-party tool called Registrator. It still exists. Basically, you can use it as a sidecar container with a different Docker container to kind of publish information about that running Docker container into a key value store or a config store like etcd or Zookeeper. So it still exists today. It still has usefulness, but having the extra moving part there really hurt us as an engineering team. It definitely bit us a couple times. And finally, the part that really took us away from Fleet was that network failures were not well managed in Fleet. So we run all of our workloads on Google Cloud platform. So something that commonly happens on such networks is that you have a network partitioning event where half of the nodes can see each other and half of the nodes can't. So whenever something like this happened with Fleet, we'd have, and then it was fixed. Upon being fixed, it would stop everything in the cluster and start everything in the cluster because it wouldn't be sure about whether the state of every other node that had just rejoined was consistent. So just to be safe, it would stop and start everything. And this was very troublesome for us providing a web service because if all the web servers go down at once, even if you have a load balancer in front of it, well, you just get straight up downtime. So that really hurt us a couple times. So after grappling with issues like those for a few months, we decided to reevaluate the container management product landscape. And we sought to re-implement our entire container deployment using one of those. As you might guess from the nature of this talk, we landed on Kubernetes. Sarah's First Plus is that it is a container management system. Actually, it has first-class configuration support for starting and stopping containers. And every time you want to run a custom workload, it has to be in terms of a container. Unlike Fleet, which we consider to be imperative, right? Start, stop, submit, destroy. Everything about Kubernetes was declarative. So rather than saying start, stop, stop, destroy, you said you upload a configuration file expressing how you want the world to be, and then Kubernetes takes that file and reads it and reads the state of what's going on to make some decisions about what to do to bring the world to the state that you've asked. So yeah, anything you can do with the system, you can express in terms of its data model. So, right, so the base unit of Kubernetes that everything's kind of built on is called a pod. It's a grouping of more than or equal to one container, one Docker container. And on top of that, the thing that we use the most is called a deployment, which is kind of that kind of system where you tell it, I want 5 replicas of this, and I want it at this tag. It also does have service discovery and exposition. So this service object is very powerful. It lets you have a consistent way to access a group of pods internally or expose them externally to the internet. And I know a lot of people in this room are very aware of what Kubernetes does. I just know that there's some newbies and wanted to make sure that everyone was kind of on the same page. So I'm also going to kind of dig in real quick to kind of technically what that looks like. So this is an excerpt of one of our deployments. The same thing, we're deploying the API server. So in the config file, you tell it what do you want to run. So there's an explicit container section saying what do you want to call the container, what's its image, and what's its command line. All of this is first class, and in this section, I've kind of abbreviated it, but there's many options that kind of line up with real Docker options, but they're like data field instead. So instead of adding a command line flag to run Docker, you're just adding a data field to describe what you want. In the next snippet, which is part of the same deployment, there's a strategy section. So this part tells Kubernetes how do you want to effect an upgrade operation that needs to be done. So you can tell it how many replicas of the new version to start at a time, and how many you can take down safely at once. So in this case, it's our HTTP API service. So we only want to take down one at a time because, again, if you take down all of them at once, bad things happen. Next, like how can I make sure the container is still working? So in the same deployment file, you can, and this is actually part of the pod configuration, strictly speaking. How can you make sure the container is still working? So you can specify a data fields, like liveness probe and readiness probe, that let you tell Kubernetes how to evaluate whether your container is stuck or frozen, or otherwise not healthy. So you can tell it to get a path on an HTTP server. That's what we do here, because it's a HTTP service. You can tell it to poke a TCP port, just like poke it and see if it gets a connection. Or you can tell it actually to run a command in the actual container. So I won't show that here. But there's basically many different ways. The system is very much encouraging you to educate it about whether something is working or not, so that the system can possibly make a change to fix that. So that helps me sleep better at night, right? Because I don't want something to just lock up and then I get a page at like 3 a.m. because I just need to like restart an API server. That's no longer a thing with these health checks. Of course, it's not like all code has these types of health checks built in, so you might have to do some work to get it there, but it's well worth it. Next, so scaling, the thing that we've been talking about a lot, that's very, very simple to do in Kubernetes. In the configuration file for a deployment, that's just one metadata field. You just say, how many replicas do you want of this? And it's an integer field. So that's all it is. It's such a well-used part of editing like a deployment or a configuration like that it's exposed on the command line. So there's a kubectl tool that allows you to perform lots of cluster manipulation. And one of the sub-commands that you have exposed to you there is kubectl scale. And all that does is edit the replicas field and put re-upload the object. And so we're using this command every day to bring our workloads, our replicas up and down to accommodate the varying levels of traffic that we get every day. Oh, that didn't work. So what you're not seeing here is once you have this all descriptive, YAML configuration file describing what you want to run, all you have to do is run kubectl, apply it, and then that just uploads the data file. And then again, Kubernetes takes that, reads it, and understands what changes it needs to make, if any, to make your changes live. Potentially none, right? So that's really powerful. If you upload the same config file 10 times, it's not going to restart everything, or it's not going to perform a 10 times upgrade of the same version to the same version. It's going to decide, okay, the system is already in this state, and do nothing. So that's very simple. Oh, well, that's why it didn't show up. All right. Well, at this point, it's pretty obvious to you that oh, we love Kubernetes and want to stick with it. So let me summarize the overall reasons why we love it, especially in comparison to Fleet. This declarative nature is really crucial to us. It's very easy to encapsulate in your head. You don't have to think, oh, I need to make this change to the config file, and then I have to do actions B, C, and D. It's just one data file containing everything about that deployment. And as I just said before, it's idempotent, so if you apply the same configuration file 10 times, nothing happens. It might make the change the first time, and then the other 9 times it's like, we're good. It's designed explicitly for scaling. You can see with that replica's metadata value that's a first-class primitive that you get from Kubernetes. Kubernetes is designed explicitly for service discovery and exposition. So this is really powerful for us because we deploy a web service. So we've been able to express so many parts of our needs just in terms of the Kubernetes service. I won't talk more about how you can actually do that much here, but you should look it up yourself. Kubernetes service, it's very powerful. And you have painless, unsurprising releases with deployment because you can tell it how you want to upgrade your workload. You can tell it, do it slowly, do it fast, kill everything and bring it all up, or kill one, bring one up. It'll just do that for you. It's got great command line tooling with kubectl, so that makes it very easy to kind of manipulate the cluster from the command line. It's well documented with good examples for everything you could really want to do. That's all on their website. And finally, we trust the team. So the original purpose of Kubernetes was to create an open source version of how Google manages their internal workload scheduling on their many hundreds of commodity machines. That's an often told story. So basically, Kubernetes started as an open source version of that, and so we trust them. It works for Google. It works for us. Not really trying to drink the Kool-Aid here, but especially as their main product is a website and a web service. Definitely work for us. Hello. So Kubernetes is still a young product. It's not totally perfect. We have just a few things to note that we think could work better in our experience as a small startup. Mostly they have to do with the schema, the config file schema that you are able to upload to it, since that's how all the features in Kubernetes get exposed to you. So first, the service object schema keeps evolving. They keep adding new ways to express similar types of things, but of course they also want to keep compatibility. So there's this gigantic pile of slightly different abstractions and data models for expressing like a pile of pods, a pile of containers. And they're called replica set, replica controller, and deployment. And you could use all three to do the exact same thing. They all continue to exist and are all continue to be supported by the Kubernetes project. I don't know if they will phase them out, but this can be very daunting for a new user who wants to jump in and be like, okay, which is the thing? Which is the best practice here? It's a little difficult. Then the second thing that bugs us a little bit is that not all service objects are declarative. So some service objects you upload once, and then if you try to make a change to it, it won't understand that, like how to make that change. So to fully effect the change, you would have to fully delete that object from Kubernetes and then re-establish it, and then it would be able to delete everything and start everything. So that's not terribly suitable for a lot of use cases. So some of the things in Kubernetes are like this, and it prevents us from using them to the way we imagine them, the potential. Finally, the service abstraction for exposing traffic to the internet on pods, it's really easy to understand. Again, you should read about it, but the way it's implemented comes with a performance penalty, so at least at the high levels of traffic that we experience. So we ended up not using the abstractions they gave us to expose our front ends. We had to kind of work around it, and we're not super proud of that, but right now we haven't explored the alternatives yet. So in addition to Kubernetes, it so happens we've been with Google Compute Engine from the very beginning. As someone else correctly mentioned in the talk, yes, they gave us some money to try out their service, and it totally worked because now we're locked in. So when Google Container Engine became a product, which was their, well, I'll talk about it in just a sec. But when Google Container Engine became a product, it was an easy decision for us to just give it a shot as part of our kind of transition away from Fleet. So here I'd like to describe what Google Container Engine gives you on top of just plain old Kubernetes. So, as I said, Google Container Engine is a service that's built on top of Google Compute Engine, which is kind of like AWS EC2. They just, a service to give you a pile of computers that are in the cloud. It runs on top of that, and they give you like templates and a Kubernetes master server that are all set up for you, and they all talk to each other already. So with one click, like I could do it right now, I could create a container cluster containing certain nodes of certain sizes. It will spin for about 10 to 15 minutes, and then I can issue a command to retrieve the information for accessing that cluster and then start deploying my workloads to it. It's really that fast. One thing that's cool is that if you're a hobbyist, it's free for small clusters. So if the cluster is less than 6 nodes large, you don't have to pay any extra. You just pay for the compute time that you're using. So you could create like a 1-node toy cluster on Container Engine, and you just pay for that like micro instance or whatever you decide to put it on. I probably wouldn't recommend putting Kubernetes on a micro instance. Let me see what else I got here. Right, so when you create a cluster using Google Container Engine, the master server is kind of not exposed to you. It's not even an instance that you get to see. It's just kind of in the sky, and when you retrieve the information for the cluster, it's just this random IP address that has your API server on it. So it's abstracted away from you, but in fact, I think that's a good thing because a lot of things are happening behind the scenes there. So here are some benefits that we get from Google Container Engine that really make the product for us. The first is that you don't have to ever worry about making the nodes talk to the master. It just worked from the very beginning. I don't even know how to start a Kubernetes cluster on bare metal from scratch to this day. We've been using Kubernetes for like a year, but we've never had to use it. The second is that that master that they give you, the master server, that's highly available by default, so they've got multiple replicas of it, and that gives you some assurance in case of spurious crashes and bugs. Third, and I think this is the most important one for us, there's some really deep integration with Google's load balancing products that you can get with Google Container Engine. And what that means is that you can create a deployment in Kubernetes, and with one extra configuration file, like a service, you can tell it to expose it on a layer 7 HTTP load balancer. You can tell it to terminate your SSL for you so that you don't have to deal with that overhead. And it will automatically point to the pods in your deployment. And all of this can happen, again, you upload the config file and it happens in 5 minutes. And that load balancing technology has taken us from 5,000 to 10,000 to 25,000 requests per second. And only once in 1.5 years has it actually let us down. So, and that time it was totally out of our hands. It was Google's fault. And they were very upset about it. Next, if you're in Google Cloud Platform, they'll also give you a Docker registry for free. It's not big, but it's one less thing to worry about. It's backed by their Google Cloud Storage, an S3-like service. And you don't pay any extra for this. You just pay for the size of the containers that are pushed to the registry. And if you saw yesterday's securing your Docker image registry for production talk, you can tell that it's not an easy task to button that up. And so just to have it done for us was very liberating. Finally, once you're set up with Google Container Engine, it's really easy for developers to get set up with accessing the cluster. When you use Google Cloud, you get this G-Cloud tool that gives you access to all the things that you provision, and one of those commands that you can run is just give me access to the cluster that I just created. So for developers, it was really easy to hit the ground running. So what could be better? So again, not a perfect product either. With any hosted product, generally the realm of complaints is that you're giving up some degree of control in exchange for having things taken care of for you. And that's certainly true about Google Container Engine. So we found that we wanted to to make tweaks, for example, to the networking parameters of the kernel, like the sysctls. We couldn't do that without like hacking the template, but in the end we did, because we're like, this is essential to our needs. So we hacked it, and I'm not very happy about it, but we hope that they come up with a solution in the future to allow tweaking these things. Next thing, when you upgrade Kubernetes, or when you upgrade the Google Container Engine clusters, there's two phases. You can upgrade the API server, or you can upgrade the constituent nodes, the servers themselves. Upgrading the master is all well and good, but upgrading the nodes can be a bit of a wild ride. We found that it did it way too fast, so it's a potential like pain point if you have a service that needs to remain up throughout your upgrade procedure. We definitely, kind of dropped some parts on the road as that was happening. So that can be annoying if you expect to have more control over upgrading your infrastructure. I hope that they come up with additional features to control the speed of upgrades. So yeah, if you're a control freak sysadmin type like me, it can be very troublesome. Finally, I mentioned earlier that when you use Container Engine, you get an API server that's highly available. It turns out, if you kind of read between the lines, that this high availability is only within one compute availability zone. So if like the entire data center goes dark, then I think you're in trouble. You're definitely screwed. Many people are screwed if that happens, but you want to have a case for that. So now that we've described how we got to the deployment story that we have today, I'd like to wrap up by making some final conclusions and recommendations to people who are trying to walk this path of like, how can I kind of make a huge product in a small startup with like very few people. The first one is to value replicable workloads from the very beginning. So again, go watch Casey's 12-factor talk if you weren't there yesterday. You have to design for this from day one, or like it won't just fall into your lap. You have to design for it. You have to invest like real time and effort to convert your existing stack to 12-factor. So the next thing is that you should use Kubernetes. We encourage it. It's great for replicable workloads that fit into containers. Make sure to analyze your use case. Make sure that's what you have. Don't try to like fit a square peg into a round hole. Don't force the issue. Not all companies will be like ours. Then, assuming that you do want to use Kubernetes and you do have a replicable workload, we do recommend Google Container Engine as a platform. It takes a lot of worry out of your hands, especially if you have few engineering staff. You don't have to worry that much about building the cluster. You don't have to worry about like Ansible and Chef automation to keep everything working right. Its price is marginal compared to the compute requirements of your organization. So if you have 20 servers, the cost of the cluster management is like a marginal cost per month. Even if you decide not to go with Google Container Engine, if you happen to go with Google Compute Engine, I really recommend taking advantage of their load balancing services. And I'm sorry. This lets you kind of focus on your business logic and kind of not worry about having like, the right config in place to accept the number of requests you're going to get. Like, people don't really notice, like people who visit your site or use your service don't really notice that you have a sweet AJ proxy front-end configuration, but they will notice if your site is down because of your shitty AJ proxy configuration. So their load balancing services have really taken us like if that was the only part of the platform that existed, we would still have gone all the way with them, because that part really made it for us. It's so much less to maintain. And yeah, so it's just a case of like, if you've got few staff, there are products out there today, like Container Engine and Compute Engine, that kind of allow you to relinquish a little bit of control to focus on what makes your product unique. So if you're interested in following our path, there are some resources that can help you learn more about Cube and Google Container Engine. Just the two websites describing those products. However, I also, if you're kind of dipping your toes into Kubernetes, I'd love to give a special shout out to Helm. So this is a project that's being done by the Days people, who are also somewhere here today. If you're just getting started with Kubernetes, they kind of have this like system of blessed configuration files that lets you kind of easily say, I have a Kubernetes cluster, and I want Postgres on it right now. And there's like accepted config files that will do this in a best practice kind of way. So it can be really an easy way to visualize like, what you can do with Kubernetes. Finally, a shameless plug. That's it for my talk, but I'd love to just put the word out there that our company, Arbor, is hiring engineers. If any of the technology that we talked about sounds interesting to you, we hire at all skill levels. We want to double the size of our engineering team by the end of next year. So yeah, don't hesitate to reach out to us if anything sounds interesting. Or just to like bitch at us about the choices we made, that's fine too. You can check out our website, you can check out our GitHub and our very small tech blog. It has exactly one article. I promise we'll get more content soon. And of course, but like today, you can have even better access to us by just talking to some of our engineers who are strewn about the conference. Can you raise your hands, Arbor people? So yeah, that's all I got. We have a few minutes for questions if anyone wants to ask anything. Yes?
You mentioned you were hitting some sort of performance issue when you were trying to scale sort of towards the end of the Kubernetes section. Can you go into some more detail about how you detected the issue and worked around it?
Cool. Okay, so the question was that we did experience a problem using Kubernetes for exposing our web service in the early days. And we found that basically using the service abstraction was not suitable. And we had to kind of wire up the front ends directly to the load balancer. So the symptom that we saw at the time was that we were using HA proxy not as kind of a first level like web server. It was basically being load balanced by Google Compute's load balancer and then going to our HA proxy for routing. What we ended up seeing in those days was that the number of sockets was being exhausted at a really fast rate and they weren't being reached fast enough. So and there was also some kind of interaction with IP tables because when Kubernetes services, the way Kubernetes services are implemented, it's like if you access this port, this external facing port on the server, I will forward you to any pod that's implementing that service in the cluster somewhere. It might not even be on this machine. And I think the use of IP tables there, may well be fixed now, caused it to stop kind of processing connections. There would be some kind of like queue level blocking somewhere that we weren't able to fully detect. But as our need was urgent, we just kind of ripped out the wiring and just, kind of configured our pod to directly listen on the port 80 of the machine that was running it. Yes?
Do you use any type of encryption between the members of a cluster or between your user control, when you control?
So the question is, and let me repeat it to make sure I get it. So it's like, where do we use encryption in our cluster?
Yeah, if you do.
So within the cluster itself, we don't use encryption for internal services talking to other internal services. But when we work with our partners, especially because we're dealing with potentially like personally identifiable information, we try to upgrade as many connections as we can to HTTPS so that the data being sent to us occurs over a secure channel. Also, there are some partners who can't do that, and so we provide different encryption for them to send kind of advertising information to us in a way that's still secure, even though HTTPS is not in use. Any more questions? I think yes, last one.
What monitoring tools do you guys use?
Oh, great question. So right now, we're using Datadog. So in our Go workload, we have a lot of stats that we write. We announce them via statsd. And so Datadog has a statsd implementation that allows us to kind of collect all the metrics and then view them using Datadog. So we have kind of charts for our backend processing rates. We have charts for how many hits per second we're getting. But we're definitely, especially after coming here today, we're looking into Prometheus. We're trying to make a conversion there because it seems to kind of implement all the things that we need in that realm. And also, it happens to be free. we're very tired of being paid out a lot of money.
Do you monitor your Kubernetes hosts themselves?
Yeah, so just for basic stuff like disk space, because right now in Kubernetes there's no enforcement over pods using disk space, and because we have lots of data coming through, there's a very real possibility of disks filling up and causing bad things to happen. So we have some basic monitoring on the hosts themselves, but yes, I think most of the valuable business metrics come from our pods.
Applications
Yeah,
themselves.
exactly, our application level
Right.
metrics. Cool. Okay, very last question since no one's kicking me out.
From the analytics perspective, just curious, are you leveraging like BigQuery and Dataflow or any of the other tool set?
So the question is, for our analytics, did we use BigQuery? And the answer is yes, especially at the very beginning. We found that at scale, we didn't want to use BigQuery for everything because it was kind of hard. Well, it wasn't hard to ETL into it, but it was kind of expensive. And so after a certain point, we needed to implement it in-house to keep costs down.
So apparently yesterday, CoreOS team announced Kubernetes operators, which is like, as I understand it from this article I'm just reading, are like little robots that can do stuff to spin up little clusters or set up Prometheus for Kubernetes.
Ooh.
So kind of related. Sorry for interruption.
Oh, no problem. This is great.
I think we're gonna start the kickoff for our workshops in another room.
Thank you.
Thank you very much, Josh.